Okay, we're finally going to talk about Gauss's Theorema Egregium, the remarkable theorem. I've been really looking forward to this lecture. It's one of my favorite topics, and nothing's going to stop me today. It may be a little bit late. I'm eager to get home. My throat is sore from hours of talking, but nothing's going to stop me. This will really be one of the highlights of this entire series, and maybe a high point of this series until we get to talk about moving surfaces, which is more exciting and is even closer to my heart. So I'm really looking forward to that. We're still maybe a month or so away from that, but now we can finally talk about Theorema Egregium. And there will be a lot of calculations on the board today. And I don't want you to think about those calculations as technical. I think they're exhilarating. I think each calculation is a journey. And I think that it's truly wonderful to be along for the ride, along that journey. And you never know whether the calculation will take you. The only thing you know about a calculation like this is that it'll take you to somewhere beautiful and somewhere where you really want to be. And the only thing that could possibly be better is to be the first one to get there. But that doesn't happen all that often anymore, unfortunately. But in any case, this will be some very elegant calculations. We'll do several of them. We'll do a couple of warm-up calculations. I think you'll enjoy them very much. And of course, we'll arrive at something that's remarkably significant, remarkably surprising, and remarkably significant. So we've actually discussed the significance of this theorem before. So before watching this lecture, I think you should watch my lecture on the curvature tensor, where I, for the first time, mentioned Theorema Egregium and talked about some of its important implications. And its implications, of course, go far beyond what we're going to talk about today. And they touch upon topology and embedded surfaces and intrinsic geometry and relativity and just a lot of amazing things. But today, our focus is on the derivation. And to me, that's actually one of the more exciting things. So I hope you truly enjoy it. Our first order of business, for me, is to redeem myself for the calculation with which I closed the last lecture. And I was eager to go home and see my wife and daughter, and I must have made 12 mistakes. One of my good friends is studying that lecture right now. He promised to count the number of mistakes I made. So I'll do it again. I'll try to do it without any mistakes. And then we'll do a couple of other small warm-up calculations. And then we'll finally derive Gauss's Theorema Egregium. And for some of the calculations, we'll actually assume that our surface is embedded in a non-Euclidean space. So we'll give up the fact that in the ambient space, the Riemann-Christoffel symbol vanishes. We'll actually consider the theorem and all of our calculations in a more general setting, because they're more revealing in a general setting, and the structure is much more evident. So let's start with the calculation that I did last time. And all of our calculations will be somehow relating related objects on the surface and in the ambient space. So we'll first relate the surface Laplacian to the ambient Laplacian. Then we'll relate the surface Christoffel symbols to the ambient Christoffel symbols, just as a warm-up exercise. Then we'll talk about the commutator on the surface, but for objects with ambient indices. And then finally, we'll relate the surface Riemann-Christoffel symbol to the ambient Riemann-Christoffel symbol. And that relationship is essentially Gauss's Theorema Egregium. It's actually a little bit more general. It has two independent equations in that relationship. One is called Gauss's Theorema Egregium. The other one is called the Codazzi equation. And the combination in its most general form that simply relates the two Riemann-Christoffel symbols, tensors, is called the Gauss-Codazzi equations. So let's get there. Let's start with the task of relating the surface Laplacian of an invariant that is defined in the entire ambient space. So the surface Laplacian applies only to the restriction of that field to the surface, to its ambient Laplacian. So if we have an invariant U, and we want to evaluate its surface Laplacian, okay, then we'll apply the chain rule here. So maybe we should denote what we're using. It'll be encoded, but maybe it'll be a good reminder of what we're using. So by the chain rule, the inner derivative can be denoted by the shift tensor contracted with an ambient derivative. And now I'm applying the product rule, and also the derivative of the shift tensor. We'll do it in one step. We get this, of course, is the normal. Review the lecture on that was called the covariant derivative in its full generality or something like that. So this will be the normal vector times mean curvature, which, as you know, is my favorite symbol, times, okay. All right, of course I forgot this. No, I didn't. I'm doing great. I'm sorry, I'm doing great. I thought that I'm back to my old habits again, making errors. No, that's great. Plus, so that's the first term, plus the second term in the product rule, where this derivative applies to this term. So, zi alpha, the shift tensor, times the times the covariant derivative, surface covariant derivative of the ambient covariant derivative of U. Okay, great. So now I will leave this term alone, and I will analyze this term by the chain rule again. By the chain rule. So let me first copy over the term that I'm leaving alone, and I will write it in this order. Mean curvature times the normal contracted with the ambient derivative. And the reason why I like putting these two terms together is because this is an invariant that can be interpreted as the normal derivative of U at the boundary plus zi alpha, z alpha need a new letter j, and ambient derivative. And let's see, so we know that, okay, so in this calculation, we're still in the Euclidean space. I'll give you a signal when our ambient space is no longer Euclidean. So let's assume that this calculation applies to the Euclidean ambient space. So we don't have to worry too much about the order of these derivatives. Because, of course, if the ambient space were not Euclidean and the Riemann-Christoffel tensor did not vanish, then these would not commute. So right now I wrote them in the order that they naturally appear, so the question of commuting has not arisen yet, but we'll see what happens in just a moment. Okay. Excuse me. Okay, so of course the next term that we'll deal with is this. Maybe I'll call this the projection formula. Please review the lecture on the shift tensor. And it will be, okay, more or less the final answer, so that I don't do too much copying. I'll just double underline this term and just put two lines here to indicate that this term comes here intact, but this term is delta plus delta ij minus ni and j. And this is the projection formula that states that this combination equals this. So it's the projection onto the surface. And then, of course, we keep grad J, grad I, U. And as I'm doing this calculation, I keep thinking to myself, am I using the fact that the ambient space is Euclidean? And I have not done that yet. And in fact, yeah, I might do it in the next step. Okay. So, continuing, we're about to pretty much write down the final answer. So I will now actually write this term in, because in the final answer we should be able to see B alpha alpha n I grad I of U plus, of course, this term, multiplying this term will simply rename J to I. So plus, and here we have the ambient Laplacian, just like we wanted. So we're indeed relating the surface and the ambient Laplacian. If I had, time and space, I would maybe write this term first, just so that they're very clearly related. Okay? Minus. And let's see what we do with this term. So we could leave it as is. And then this would be actually valid even if the ambient space was Euclidean. Yeah, it was not Euclidean. But because right now we're not so focused on that, and we just want a pretty answer, let's assume that the ambient space is Euclidean, and then we can switch the order of these operators. I actually think, now that I'm thinking this through, I don't want to focus on that right now, but I actually think that because it is multiplied by a symmetric tensor, the part that would be proportional to the Riemann-Christoffel tensor that will arise from swapping these two would be skew symmetric, and in combination with this tensor, it will actually vanish. So I actually believe that what I'm about to do is valid even if the ambient space is non-Euclidean, is a Riemann space. Okay? So, but assuming that it is, there is nothing more that I would even have to say, except that I'll write both of my normals with the lower indices and both of the derivatives with the upper indices. And I will do it without my characteristic gravitational drop. All right, minus n I n j derivative I derivative j of u. All right, and we have succeeded at the task of relating the surface Laplacian to the ambient Laplacian, and the two additional terms that arose was the normal derivative of u multiplied by mean curvature. So the curvature of the surface plays a vital role. It's very gratifying to get mean curvature show up, minus the term that we actually learned to interpret as the second order normal derivative of u. Okay, fantastic. So we've succeeded at our first task. Our next task will be to relate surface Christoffels to the ambient Christoffels. And even though it is not directly helpful in our major calculation, it is very similar in spirit to what we'll be doing when we're deriving Gauss's Theorem Egregium. So it'll be a very useful discussion. All right, let's pause to erase the board, and we'll continue. Okay, we're marching towards Gauss's Theorem Egregium, and our job now is to relate the surface Christoffels to the ambient Christoffels. I've just written down the definition of the surface Christoffel. The only thing that's left is to relate the surface basis to the ambient basis. And of course, that's done with the help of the shift tensor. So we just have to plug that relationship in, and the relationship we're looking for will pretty much present itself. Okay, so S gamma equals ZK Z gamma K, the shift tensor, dotted with the derivative of S alpha, which is Zi, Z, which is Zi alpha. Okay, let's continue to the next line and find out what we're going to have. So I will say a few things here so we can save one step. I think that as you're practicing these exercises, these calculations, you should not skip the step. But this will be first analyzed by the product rule. And then the second term in the product rule will be a final term. There's nothing else you can do with a partial derivative of the shift tensor. It is what it is. After all, the Christoffel symbol is all about partial derivatives, not covariant derivatives. Okay, but the first term will be the derivative of the basis element with respect to the surface variable. And of course, this basis is defined in all of space. It can be expressed as a function of the ambient coordinates and then differentiated by the chain rule. And one of the first derivatives, so by the chain rule, it'll be dzi, this term, dz beta, excuse me, okay, half a step back. There's no such thing as z beta, so it's easier to write these things than to say them, and it's probably even harder to hear, so maybe you want to visualize what the term will be, but it'll be dzi, dzj, ds beta. That's how the chain rule will go. And of course, dzj, ds beta is by the very definition the shift tensor. So here is what we're going to have. Ck, z gamma k, the shift tensor, dotted. I've talked about this in the book. It doesn't matter where the dot goes, as long as it's between the two vectors that are being dotted. And by the product rule, the first term will be, as we discussed, d, c, I. D, z, j. dzj, ds beta, which is z, j, beta. And then the first term is unchanged, zi alpha, plus this term, zi, and then the derivative that, like I said before, there's nothing you can do with. It's a primary object, it's a terminal object. We're going to be left with this object. Okay. And now we're almost done. So once again, maybe I'll just say words in place of writing things on the board. But here's the nice thing. If you think about what this object is being dotted by this zk, and of course, by the very definition, actually, in the ambient space, that's not taken as the definition. It's one of the consequences, one of the elementary consequences of the definitions. But this combination is the ambient Christoffel. And ambient Christoffel is being contracted with the three shift tensors. So gamma, it's almost like the ambient Christoffel is being, gamma k. It's almost like the ambient Christoffel is being projected onto the surface in each of its dimensions. So let's write it in attractive alphabetical order. Z I alpha, Z J beta, Z gamma, Z gamma K. Plus this term, plus this combined with this. So let's figure out what that is. So I'll put a plus here, because I ran out of space. And here we have zk dotting zi, which of course is the Kronecker delta ki, which will simply rename this k into I. And now I'm realizing that I have just enough space to squeeze that term in. Plus zi gamma d z I alpha d s beta. Beautiful. So, in relating the surface Christoffel with the ambient Christoffel, there's a projection term. It's the ambient Christoffel projected along each one of its dimensions, plus this very interesting term, which almost looks like, if you think about the shift tensors as the components of the surface basis elements, then this formula almost looks like this, right? Because it's the components of this right there being dotted, because there's this, tensor equivalent of the dot product with the components of this. And of course, it's exactly that interpretation if the ambient coordinates are affine, only possible when the ambient space is Euclidean, but this entire discussion was Euclidean because we were using these objects. All right, but if that's the case, if the ambient coordinates are affine, then this term goes away completely and we're only left with this term. So in many practical applications when the ambient space is Euclidean and the chosen coordinate system, especially on the computer, is Cartesian, it happens maybe too often, the Christoffel symbol can be calculated by this simple calculation. And take my word for it or derive it on your own if you'd like. That's an even more technical calculation and therefore more exhilarating as far as I'm concerned. But this can be derived for general Riemann spaces. The ambient space need not be Euclidean, and you will get the exact same relationship. It's quite nice. Okay? We'll continue our march towards Theorem Egregium, and after the pause and the clean board, we'll talk about the surface commutator for objects with ambient indices. You'll see what I'm talking about, and as preview, we'll take one small shortcut there, which I regret, but we have limitations of time and space. Okay, see you in just a few moments. Thank you. All right, I did a lot of writing while the camera was off. This is just a reminder of what we know about commutators so far, and I just have a few words to say about all of this. So this is what we originally derived in the ambient space, that the commutator, which if these were partial derivatives would be 0, with covariant derivatives, not so much anymore, would be, if it was just one index, we'd just have sort of this one term. If it was the bottom index, it would be a term similar to this one. But the more indices we have, there is a Riemann-Christoffel term for each index. And of course, the point back when we were deriving this was that we're doing this in the Euclidean space. And there were two great arguments for why these derivatives commute and why the Riemann-Christoffel, equivalently, why the Riemann-Christoffel tensor vanishes. But for the moment, I invite you to imagine a situation where the Riemann-Christoffel symbol doesn't vanish. This can happen. You can imagine two situations. One, very easy to imagine. The other one takes a little bit more time getting used to. So one situation that you might consider right now is that we're actually not in the Euclidean ambient space, but on the surface of a sphere. And what we've been calling a surface so far is just a contour on the sphere. So the sphere is not a Euclidean space, but we're now calling that our ambient space. And this is the world of the surface of the sphere. But what we've been calling the surface, a surface, is now just a contour on the sphere. And it has its own commutator, which works according to this rule, with its own Riemann-Christoffel tensor. And of course, this is completely equivalent to this, because the derivation would be the same. Everything would be exactly the same. It's a complete analogy. They're both intrinsic types of things, and once we have this, we automatically have this. So there's no mystery there. So that's the situation I'm inviting you to consider. Okay, so that one was the one that's easy to imagine. The one that's a little bit harder is, yes, we're in a three-dimensional ambient space, but it's no longer Euclidean. In other words, the metric tensor did not arise from a dot product and that dot product considered in some sort of coordinate system. What we have is a space, a coordinate system, and at each point in those coordinates, someone had arbitrarily imposed a metric tensor field. And that metric tensor does not necessarily satisfy the equations that would make the Riemann-Christoffel symbol vanish. Right? So, not for any metric field can you imagine a coordinate system for which the metric tensor will be what you've arbitrarily assigned. Because the metric tensor in Euclidean spaces needs to be such that when you use it to compute the Riemann-Christoffel tensor, it vanishes. So if you start with a three-dimensional space, I would be hard-pressed to give you a precise definition of what it is, other than to say that it's Rn or some more formal, complicated structures that exist in modern geometry and topology. I definitely don't want to go into that. But just imagine that we have some kind of what you think of as three-dimensional space, and someone had arbitrarily assigned a metric tensor at each point. And if that was done, you use the metric tensor to compute the Christoffels, and therefore the Riemann-Christoffel symbol, and whatever it turns out to be, that's what it turns out to be. That's a Riemann space. So we haven't talked about Riemann ambient spaces, but for the purpose of this derivation, I could have done it all with an Euclidean ambient space, and it would not be as much fun, and it would not be as general and as structured. So all that Gauss-Codazzi equations are is relating this object to this object. Just like a moment ago, we related the surface Christoffel to the ambient Christoffel symbol. So our task now is to relate this to this. But we have an intermediate task that is, number one, interesting in and of itself, and number two is a crucial step in determining the ultimate relationship between this and that. Between this and that. And that is to ask the question, what is the commutator when applied to a tensor with an ambient index, such as the normal? And then later, of course, to the shift tensor, because a shift tensor would have one of these and one of these, so it would have one of these terms, but how do you treat this index? That question we have not answered. And we'll now actually give an answer that actually happens to be ultimately correct, but we'll cheat in obtaining it just to obtain it in a shorter way. For the longer way, I'm thinking very quickly as I'm talking, do I talk about this in my textbook? I may not, because I think, why wouldn't I? I'm not sure. If I haven't, I probably should. But I'll check and maybe put the answer in the comments. So here's the shortcut that we'll take. So in order to evaluate this commutator, this tensor need not be defined in the entire ambient space. It might only be defined on the surface, like the normal, and this would still be a perfectly legitimate question demanding an answer. Okay, but just for the ease of derivation, let's assume that this object is actually defined in the entire ambient space. We'll be deriving a lesser result, and it just happens to be an answer that's true in full generality. Okay, so we'll assume that this is actually defined in the entire ambient space. And the reason that helps is because we can use the chain rule. That's the only reason why. Okay, and when we use the chain rule, well, I don't want to say, I'm about to erase the board, and we'll use what I was going to say is that using the chain rule just makes everything much shorter. So let's just find out what this expression is, even though our derivation is not 100% kosher. But we'll live with it because we have our sights on Gauss's Theorem Egregium, and I'm determined to get there today. It will be a very short calculation, and let's do it. Okay, let's consider just half of that commutator, and then we'll be able to visualize what happens when the two indices alpha and beta switch, and we'll be able to subtract one term from the other. So, once again, we're assuming that this is defined in the entire ambient space, so we're able to use the chain rule. And we have Z, I guess J is a good choice of letter, Z, J, beta, the derivative sub j of tk, okay? And now, by the product rule, what we have in this term is, of course, b alpha beta and j, and j grad j t grad again. I'm calling it grad, but maybe I have enough time to say covariant derivative sub j. And the second term is the surface derivative applied to this, so plus z j beta is unchanged. And then I'll just use the chain rule right away, which will be z I alpha, the derivative sub I, the derivative sub j of t k. Okay, we're actually almost done, because now what we would have to do is repeat this calculation for when alpha and beta trade places. But then we can just go to the answer and see what happens in the answer when alpha and beta trade places. And of course we find that alpha and beta would trade places here. And this term, and of course the important thing here is that the curvature tensor is symmetric in it when it's written in the covariant form. That's great. And what will happen here? Well, actually, let's do a little bit of work on what will happen here. So z alpha and beta will trade places. Excuse me, alpha and beta will trade places. So we'll have j alpha z I beta grad, again, covariant derivative sub I, covariant derivative sub j t k. Fantastic. And now, just so that I can compare these terms as best I can, I will, in this term, do the following. First step is renaming. So I will rename I into j and j into I. So that, of course, is a perfect valid operation with dumb indices. So let's just see. So j becomes I becomes j. This was I, it becomes j, and this j becomes I. And then let me also write, well, I can just, actually we're done, because what I can actually do is just imagine these in nice alphabetical order. That's all I want to do. I want to imagine these two terms in nice alphabetical order, in which case these two terms are the same, and when we subtract this with alpha and beta switched, this term will be cancelled, and this term will be able to factor this out, and in parentheses, we would have what would have been 0 in the Euclidean space. Of course, now we're assuming that the ambient space is not Euclidean, so this difference will vanish. In fact, it'll simply produce, from what I had on the board before, the ambient Riemann-Christoffel tensor, which is kind of exactly what we want. So we can go actually straight to the conclusion. And the conclusion is that the derivative sub alpha, the derivative sub beta, minus the derivative sub beta, the derivative sub alpha, equals. So this will produce the Riemann-Christoffel symbol, of tk, of tk equals. So I'm just trying to figure out what order to write this in. So maybe we'll just write it in the order just as we see it. So it will be z I alpha, z j beta. We're getting something reminiscent of the chain rule. It's sort of like the ambient relationship projected, which is not surprising. R, K, M, I, J, T, K. And now, this is the final answer. It deserves to be boxed. And now we know what to do for the surface commutator of an object with the ambient index. And while our derivation was not valid for objects defined only on the surface, the final answer is perfectly valid. The final answer is perfectly valid for objects defined only on the surface, like the normal or the shift tensor. And it's actually the correct answer, even though the derivation was technically not quite valid. And I invite you to figure out what will happen if this is a covariant index. You can almost see what's going to happen. And for combinations of surface and ambient indices, and you'll find out that it's just like for every index, you'll have to have a Riemann-Christoffel term. By itself, the surface Riemann-Christoffel term for surface indices, and a term just like this for ambient indices. So we're now finally ready to derive Gauss's Theorema Egregium. And I'll pause, erase the board, and explain the strategy to you when I come back. Thank you.